Have you ever put on a pair of headphones, flipped a switch, and felt the entire world just vanish? What if I told you your headphones aren't just blocking sound, they are literally creating anti-reality? How does a tiny piece of plastic delete a roaring jet engine from existence? To understand how we delete reality, we first have to understand what reality actually is when it comes to your ears. When you are sitting on an airplane, that deafening roar of the jet engines isn't just a concept in your brain. It is a violent physical event happening in the air around you. Sound is nothing more than a pressure wave. Imagine a giant slinky being pushed and pulled. The airplane engines are violently shoving air molecules into each other, creating areas of high pressure where molecules are squished tightly together, and areas of low pressure where they are pulled apart. In physics, we call this a longitudinal wave. These invisible walls of high and low pressure travel through the air at roughly 767 miles per hour until they smash into your eardrum, vibrating the tiny bones inside your skull. So, what if we tried to stop this the old-fashioned way? What if we just shoved a bunch of thick, dense foam between our ears and the outside world? That is called passive noise isolation. Brands do this all the time with heavy, bulky ear cups. But here is the problem. Low-frequency sounds, like the deep rumble of an airplane engine or the hum of a train track, have massive, drawn-out wavelengths. Some of these sound waves are literally dozens of feet long. They do not care about your foam. They will travel right through the plastic, right through the dense foam, and right into your skull. To stop them purely with physical mass, you would need to wear earmuffs the size of a refrigerator. Since that is completely impractical, engineers had to come up with a way to fight physics with physics. The theoretical idea of canceling sound was actually patented way back in 1933 by a German doctor named Paul Lewig. He theorized neutralizing sound in ducts using phase-advancing waves. But it was just theory. The technology of the 1930s wasn't nearly fast enough to pull it off. The real turning point happened decades later, in 1978. A brilliant acoustic engineer and MIT professor named Dr. Amar Bose was on a flight from Zurich to Boston. He was handed a pair of early electronic headphones by the airline, but the plane's engine noise completely drowned out the music. In a moment of absolute genius, he pulled out a notepad and began calculating the physics of exactly how a headphone could create a counter signal to destroy the noise before it hit his eardrum. That single flight birthed the modern active noise cancellation, or ANC, industry. Today, giants like Bose, Sony, and Apple dominate this space, using microscopic chips to perform acoustic miracles in real time. But how does that miracle actually begin? It all starts the exact millisecond you press the power button on your headphones. That simple click physically closes an electrical circuit, allowing direct current from a tiny, rechargeable lithium-ion battery to flood the internal motherboard. This burst of energy immediately wakes up the brain of the headphone, a specialized microchip called the Digital Signal Processor, or DSP. But the DSP is blind and deaf on its own. It needs sensory organs to know what reality looks like outside your headphones. So, the battery power routes outward to the exterior shell of the ear cups, waking up incredibly sensitive, microscopic microphones. Most modern premium headphones use what is called a feed-forward microphone system. This simply means these mics are placed on the outside of the headphones, fully exposed to the harsh, noisy world. Let's slow time down to an absolute crawl. The jet engine fires a massive, high-pressure sound wave directly at your head. Before that wave can even reach your ear canal, it crashes into the thin metallic diaphragm inside the feed-forward microphone on the outside of the ear cup. This high pressure physically pushes the microphone's diaphragm inward. Instantly, the microphone translates that physical pressure wave into an electrical signal. An exact, analog copy of the chaotic noise outside has now been captured in electrical form. The race has officially started. The physical sound wave is still traveling through the air, stubbornly pushing through the plastic shell of the headphone, while the electrical copy of that exact same noise is already sprinting down a microscopic copper wire toward the audio processor at a substantial fraction of the speed of light. Because electrical signals zip through copper wiring incredibly fast, the headphones have bought themselves a tiny, crucial window of time. Sound waves traveling through the air move at roughly 1,125 feet per second, but electricity moves millions of times faster. In the microscopic gap between the physical sound hitting the outside of the plastic ear cup and bleeding through to reach your actual eardrum, the headphones have fractions of a millisecond to perform an act of absolute digital wizardry. The raw electrical copy of the jet engine's roar hits a microchip gateway called the analog-to-digital converter. Think of this component as a lightning-fast translator. It takes the messy, fluctuating electrical voltage coming from the microphone and slices it up, translating it into a crisp, mathematical language of ones and zeros. Now, the brain of the operation, the digital signal processor, can finally see the noise. The DSP instantly maps out the anatomy of the sound wave. It registers exactly where the high-pressure peaks and low-pressure valleys are located. Here is where the absolute magic of physics comes into play. A phenomenon called destructive interference. A brilliant British polymath named Thomas Young first demonstrated this concept with light in his famous double-slit experiment back in 1801, but the exact same mechanical rule applies to acoustic waves in the air. To understand destructive interference, imagine you are standing on a perfectly flat beach. A wave of water rolls in, creating a mound of water exactly 1 foot above the flat surface. Now, what if you perfectly timed an identical, inverted wave, a deep trench exactly 1 foot below the surface, to crash into that mound at the exact same moment? The mound of water physically fills the trench. The result isn't a massive splash. The result is a perfectly flat, calm surface. The two waves utterly destroy each other. The DSP inside your headphones acts as the ultimate wave maker. It takes the digital profile of the roaring jet engine and essentially multiplies it by -1. It generates a perfect mathematical mirror image of the noise. Wherever the real sound wave has a high-pressure peak, the DSP calculates an artificial low-pressure valley of the exact same size. Wherever the real sound has a valley, the DSP plots a peak. This mirrored profile is the anti-noise. But what if the engineers decided to use cheaper, slower computer chips to save money? What if this mathematical process wasn't instantaneous? If the headphone's timing is off by even 1/10 of a millisecond, the peaks and valleys of the anti-noise won't line up perfectly with the real noise. Worse, if the timing is so bad that a peak of the artificial wave accidentally aligns perfectly with the peak of the real wave, you trigger what is called constructive interference. Instead of deleting the jet engine, your headphones would accidentally combine the waves, doubling the volume and blasting a deafening, amplified roar right into your ear canal. This catastrophic failure loop is exactly why truly great ANC technology took decades to perfect. The processor doesn't just invert the wave, it must mathematically predict exactly what the wave will look like by the time it travels through the plastic shell and reaches your ear. Fortunately, premium headsets calculate these phase inversions hundreds of thousands of times per second, without breaking a sweat. Once the digital anti-noise profile is perfectly calculated, it is instantly rushed out of the processor and into a digital-to-analog converter. This chip does the reverse translation, turning the mathematical ones and zeros back into raw, pulsing electrical voltage. But this time, it is not a copy of reality. It is a highly weaponized countersignal, specifically designed to assassinate the jet engine noise. This electrical anti-signal is immediately injected into the copper voice coil of the headphone's internal speaker driver, located right next to your ear. The digital math now has to become a physical reality. The voice coil sits suspended inside a powerful, permanent magnetic field, typically generated by high-grade neodymium magnets. As the anti-noise electricity surges into the coil in a fluctuating pattern, it transforms the copper wire into a rapid-fire electromagnet. This creates a violent magnetic reaction. The voice coil begins rapidly pushing and pulling against the permanent magnet, translating our anti-reality signal into pure kinetic motion that thrusts the speaker cone forward and backward with astonishing precision. This rapid vibration acts like a microscopic piston, physically shoving the air molecules inside the enclosed, airtight space of your ear cup. The speaker driver is now actively generating a brand new, entirely physical sound wave, the anti-noise. At this exact fraction of a millisecond, the original, physical sound wave of the roaring jet engine finally manages to bleed through the plastic housing and dense memory foam of your headphones. It enters the small pocket of air trapped between the headphone speaker and your eardrum. But it is no longer alone. The anti-noise wave, perfectly inverted and generated by the speaker driver, is already waiting for it. The two physical waves slam into each other in the air, just millimeters from your ear canal. When the high-pressure wall of the jet engine noise collides with the mathematically engineered low-pressure trench of the anti-noise, they undergo destructive interference, neutralizing the pressure fluctuations almost entirely. But here is where we run into a fundamental, unbreakable law of the universe. Sound is not just a mathematical concept. It is physical, mechanical energy. It is the physical mass of air molecules moving and transferring kinetic momentum. The first law of thermodynamics, formally established in the 19th century by pioneering physicists like Julius Robert von Mayer and James Prescott Joule, strictly dictates that energy cannot be created or destroyed. It can only be transformed from one state to another. So, when this massive, violent acoustic energy of the jet engine is suddenly deleted from your reality, where does all that kinetic energy actually go? It does not just vanish into the void. When the high-pressure air molecules of the real noise slam into the artificially created low-pressure pocket of the anti-noise, the resistance and friction of the colliding air molecules cause the kinetic energy of the sound to convert directly into thermal energy. The mechanical energy is dissipated as heat. Do not worry, your headphones are not going to burst into flames. The amount of acoustic energy in even the loudest jet engine roar is incredibly small when converted to pure thermal output. The temperature increase inside the ear cup is so completely microscopic, perhaps a fraction of a millionth of a degree, that human skin cannot possibly detect it. But on a purely physical level, your headphones are literally converting the deafening noise of reality into a tiny, harmless puff of microscopic warmth. But what if the system simply stopped here? What if we only relied on the outside microphone to guess what the noise would look like once it got inside? The problem is, every single human head is physically different. A person wearing thick-rimmed glasses, someone with a large jawline, or even someone wearing earrings will physically break the perfect seal of the memory foam ear pads. If this physical seal is broken, outside sound leaks into the ear cup differently, altering the acoustic environment in chaotic ways that the outside microphone could never predict. If the system relied purely on that outer microphone, the noise cancellation math would constantly fail, letting annoying low-frequency rumbles leak right into your eardrums. To fix this fatal flaw, modern engineering powerhouses like Bose, Sony, and Apple integrated a second, entirely different microphone directly inside the ear cup, positioned mere millimeters from your actual ear canal. This is called a feedback microphone, and it is the crucial second half of what the industry calls hybrid active noise cancellation. While the outside feed-forward microphone acts as the early warning radar, this inside feedback microphone acts as a ruthless quality control inspector. Its sole purpose in life is to listen to the exact same pocket of air that your eardrum is listening to. It continuously monitors the immediate aftermath of the microscopic acoustic collision. If the destructive interference was perfectly executed, this internal microphone should hear absolute silence. But if the arms of your glasses caused a tiny sound leak, the internal microphone instantly detects the surviving noise that made it past the first line of defense. It immediately captures this leftover audio, converts it back into an analog electrical signal, and fires it straight back to the digital signal processor. The DSP analyzes the error in real time, recalculates a brand new, highly adjusted anti-noise profile to wipe out that specific leak, and sends an updated, hyper-accurate correction signal back through the circuitry to the speaker cone in a fraction of a millisecond. This closed-loop system is constantly checking its own homework, adapting to the exact shape of your skull, your hair, and your jawline in real time, literally thousands of times every single second. But what if you actually want to listen to a song while all of this is happening? Here we run into a massive, fundamental engineering dilemma. If the internal feedback microphone's entire job is to listen for any sound pressure that shouldn't be inside the ear cup and trigger the processor to destroy it, why doesn't the headphone accidentally destroy your own music? To the internal microphone, a booming bass drop in a Daft Punk track looks exactly like a high-pressure noise wave from a jet engine. If the system was not carefully programmed with a clever workaround, it would ruthlessly delete the very song you are trying to enjoy, treating your favorite playlist like a hostile acoustic threat. To prevent this, the digital signal processor has to perform yet another layer of advanced mathematics. The processor is the exact same chip that is currently receiving the wireless Bluetooth data from your smartphone. It already knows the precise digital profile of the music you are trying to play. So, before the processor accepts the error report from the internal microphone, it mathematically subtracts the exact acoustic profile of your music from the microphone's incoming feed. It essentially creates a deliberate, calculated blind spot. The system is programmed to completely ignore the pressure waves created by the song, isolating and targeting only the chaotic, unauthorized pressure waves leaking in from the outside world. Now, the system must merge these two vastly different tasks into one final physical action. Inside the circuitry, we have two distinct electrical signals moving simultaneously. First, we have the pristine, uninterrupted digital audio of your music streaming in from your phone. Second, we have the incredibly complex, constantly shifting, hyper-calculated anti-noise signal that the DSP just generated to kill the airplane engine. The microchip takes these two completely independent electrical streams and fuses them into a single unified voltage signal. This final master electrical signal is blasted through an internal amplifier and pumped directly into the speaker's copper voice coil. The speaker cone is now forced to vibrate in a bizarre, incredibly complex, multi-layered dance. It is simultaneously pushing the air to create the exact high and low pressure waves required to recreate the beautiful melodies and thumping bass of your music, while simultaneously thrusting out the exact, mathematically inverted pressure waves needed to invisibly assassinate the droning hum of the airplane cabin. The speaker cone is doing two entirely separate physical jobs at the exact same time, moving back and forth with microscopic precision to play reality and delete reality simultaneously. This constant, high-speed physical labor is exactly why turning on the active noise cancellation feature drains your headphone battery so much faster. The system is actively spending electrical energy to physically fight the atmosphere. The fact that a thin piece of plastic and a tiny microchip can perform this physical feat. In the span of a single millisecond, microphones capture the chaos of the outside world. Analog signals are translated into digital math. Algorithms map the physics of destructive interference. Amplifiers turn that math back into raw voltage. And powerful electromagnets violently punch the air to create an acoustic black hole. The next time you sit down in a noisy environment, put on your Sony, Apple, or Bose headphones and flip that little switch. Take a second to appreciate the sheer, invisible violence happening just millimeters from your eardrum. You are not just putting earplugs in and turning down the volume of the world. You are actively deploying an army of custom-built, mathematically inverted pressure waves to physically crash into the atmosphere, turning the chaotic noise of reality into harmless, microscopic heat. You are commanding a high-speed digital processor to conquer the laws of fluid dynamics, leaving you entirely alone in a perfect, manufactured pocket of absolute silence.